This video is part of the lecture for multivariable calculus, and we are going to talk about dot product and the properties of dot products and 4 applications of dot products for computing the angles between two vectors, detecting orthogonality, and finding projection of a vector onto another vector and the work done by a vector. So let me start by defining the dot product. First, we know how to add vectors, how to multiply a scalar to a vector, and now we want to talk about multiplying two vectors. There are 2 ways to multiply two vectors together. One of them, it's called dot product. We show it by u dot v, and the answer for this would be just a number. Or we have cross product. We show it by u cross v, and the answer for the cross product would be a vector. In the next video we're going to talk about cross product. But for the dot product, so dot product, sometimes we say scalar product, or sometimes we say inner product. It's what we have. If we have 2 vectors a dot b, the vector a with the components a1, a2, and a3, and the vector b with the components b1, b2, and b3, okay, the dot product would be a1 times b1, a1, b1, plus a2, b2, plus a3, b3. Since the components are just numbers, we multiply numbers together and then we add them up. That's why the answer for a dot product would be just a number. Geometrically, what do we have? So geometrically, if we have a vector a dot product with the vector b, okay, it is a, the length of a, times the length of b times the cosine of the theta angle between two vectors. So this is, this is vector a, for example, and then I have a vector b here, and theta is the angle between these two. So a dot b would be the length of a, the length of b, and the cosine of theta angle between these two. Okay, so let's talk about properties of dot products. Properties of dot products. The first one is that the vector a dot product with the vector a itself, it would be what? The vector a with the components a1, a2, a3, dot product with itself a1, a2, and an a3. Okay, so I get a1 square plus a2 square plus a3 square. If you remember the magnitude of a vector, this is the formula for the length of a square. Okay, so a dot a would be the number that is equal to the length of a square. Then the second property is that the dot product is distributive over addition. So a dot product with b plus c, it would be a dot b plus a dot c. Okay, you can write the components of each one of them and then write definition of dot product, and then you will see. So we're gonna say that dot product is distributive over addition. Third property is that the dot product is commutative. A dot B is equal to B dot A. Why? Just write the components and then write definition of dot product. Since the product of numbers are commutative, then the dot product is commutative. And the fourth property is that dot product is not associative. What it means that A dot B dot product with C, it's not equal to A dot product with B dot product with C. Okay, why is that? Because B dot C is just a number. It's the dot product, it's a number. So I have a vector A dot product with a number. It's not possible. The dot product is defined on two vectors. How about here? The same idea. I have a number in here. I cannot multiply it by a vector. Okay, I cannot have the dot product with a vector. So for the dot product, I have to have two vectors. So it's not associative. Okay, good. Then let's talk about applications of dot products. The first one is to compute angles between two vectors. So computing angles between vectors. So if I have a vector A and I have another vector B, and if I have theta, the angle between them, then theta, the angle theta, is given by using the geometric definition of the dot product. Cosine of theta would be A dot B divided by the length of A times the length of B. Okay, so all I need to do is to find the dot product in here, which is just a number, find the length of A, multiply by the length of B, and find the fraction. It would give me the cosine of theta. The second application would be detecting orthogonality. Okay, we say that A, the vector A, is orthogonal to the vector B, okay, if and only if the angle between them is pi over 2, right? And we know that cosine of pi over 2 is equal to 0. Therefore, using the geometric definition, we are going to say that A dot B is equal to 0. The number is 0. So it doesn't have any meaning that we have two vectors orthogonal to each other in a space. So if we have a vector and another vector in here, we cannot say what is the definition. That's why we say that definition of two vectors to be orthogonal to each other is to have the dot product of them equal to 0. That's why we use this as a definition. Okay. Then the third application is to find projection, orthogonal projection of a vector B onto a vector A. Okay, so assume that I have a vector A in here and I have another vector B in here. Then I have theta in here, the angle between them, and then this vector in here is called orthogonal projection of B onto A. Okay, so what is the length of projection of B over A? So as you see that this notation in here, projection of B over A, this is the notation that we use to show the projection vector, this vector in here. So the length of A, since I have a right triangle in here, and then I have the length of B in here, the length of this vector, the hypotenuse is the length of B, so the length of the projection would be equal to the length of B cosine of theta, right? And now what is the vector projection of B over A? I know that this is the length, so the length of this vector is this. Now I just need to put this vector in the direction of A, so that's why I'm gonna multiply this number in here, which is the number length B cosine theta. This is just the scalar, this is just a number. I'm gonna multiply it by the direction of A. How we show the direction of A? The vector A over the length of A. This vector is actually the unit vector. This is the unit vector along A. So whenever that you want to find the actual direction of A of any vector, write the vector divided by its length, and as you see, this vector in here would be the length of it. This is just a number, a positive number, and then the length of A, if I put in here, that's why I get 1. So this is a unit vector, and the direction of that, since the length of A is just a positive number, the direction of that would be the direction of A. Okay, so I'm gonna simplify that. I have B and then cosine theta, and then I have A over the length of A. So what I'm gonna do to find kind of easier notation, I'm gonna multiply it by the length of A divided by the length of A. Okay, and now as you see, this and that together, they would be the dot product. So it would be A dot product with B, and then I have the length of A squared, and then I have the vector A. This is just a number, this is just a number, so it's a scalar times A. This is the vector projection of B onto A. Okay, so this is the actual vector orthogonal projection, and we use the dot product to find that, and the length of that would be this. Okay, good. Then we're gonna say that another application, the fourth application, would be the work done. So assume that we have just a mass in here, and then we have a vector F, it's just like a force, and then we have vector vector d for the displacement. So f dot d would be the work done by vector f in the direction of d. So that was all the applications of the dot product, and on the next video we're gonna have some examples for each one of the applications and the dot products.